Okay, so I hope you can see my lecture slides. Okay, good. So last time we were discussing about the idea of memory hierarchy. Now the idea of memory hierarchy, and we have got application processors, and it has got just like in your laptop or in your mobile, and you have to feed the data or feed the instructions to the processor very quickly. And there are problems that if you've got a huge memory, then finding the right address either for instruction or for data would take long time. So you have to have memory hierarchy. And memory hierarchy, we saw that the memory which is closest to the processor is a very small but very fast memory. And as we go away from processor, then the size of the memory starts increasing, but the speed of the memory, when I say speed, means speed of the access to the memory, starts decreasing. And when it reaches your hard drive, I mean, the size is tremendous in terms of terabytes, as opposed to your first level cache, which is of few KBs. But the speed of access is of the order of milliseconds as opposed to a nanosecond or less in your first level cache memory. Okay. So to make the idea of cache a success, two things are working in our favor, or we have to make sure that two things are in our favor. The first one is temporal locality, and second one is spatial locality. Temporal locality says that if you have used an instruction or a data in say close in current time, just a little while ago, then chances are that you will use it again. And that whole idea is based on loops. That in loops, 1, 2, 3, 4, 5, 6. Again, you go back to 1. So I mean, you have used instruction number 1 just a short time ago, and the chances are that you will use it again. So that is called principle of temporal locality. And spatial locality is that when you have written a program, and normally it descends step by step. And after instruction number 1, it is instruction number 2. After 2, it is number 3 and 4 and so on. So this is what we drew last time. And two things. This temporal locality and spatial locality helps us a lot in designing our cache memory. So once again, I'm telling you, if you write a program which does not believe in temporal locality or at least in spatial locality, I mean, your cache architecture is going to be a total mess. In fact, it is going to cause you much more problem than not having any hierarchy, just having one big blob of memory. Because random access would take away a lot of your time. So, and that would be like if you have written a lot of go to or jump statement that jumping from instruction number 1 to instruction number 20 to instruction number 50, so on and so forth. So that is something which can cause a problem. Now, memory hierarchy, we have seen that you have got in cache memory 3 levels. I mean, in modern processors, L1, L2, L3. Then you have got main memory, which you call as RAM. And then there is secondary memory, which is virtual memory, or it's also known as virtual memory. You can call it hard drive. So this is how it is. So this is the final picture. And your virtual memory, your hard drive is over here. I mean, that is the domain of operating system. So this is your processor. Processor has got 2 independent caches. The first level cache, they're always independent. So you've got L1 instruction cache, or you can also write in short one as L1 $. And this is for instruction. So L1, in fact, better to write it as instruction cache, and this is L1 for both, and this is data cache. So once again, I told you the $ means cache, So people like to write it in short for cache, you write $. As you see that L2 is much larger than L1, both instruction or data. In fact, it is greater than both of them combined, but it's a unified cache. That means it has got both instruction and data inside it. And and after L1, L2, L3, main memory, and hard drive, they're all unified. That means it can contain both data and instruction. Okay. So now let us start the whole idea of caching. Now, we saw earlier that your main memory is much larger than your cache memory, right? Main memory, let's say your RAM. I mean, take your example. In your laptop, you may have 8 GB of RAM, and your cache, you may not have checked, but it might be 8 KB or 16 KB or 64 KB. So, I mean, there's a huge differential. So how do you map the address from one to the other? So I've shown a toy example here, and I will develop it for you. Okay. So let us say you've got a toy cache memory, and it has got only 4 slots. So you can store only 4 words, right? Okay. So this is your cache. And you have got only one level of cache, so no need to call it L1, L2, L3. It is just cache. And your main memory has my drawing is not good, but please forgive me for that. So there are like 16 slots. I'm not drawing all the slots, but just assume it is 16. You're starting from 0, 0, 0, 0 to 1, 1, 1, 1, right? 16 slots. And this is starting from 0, 0, 0, 1, 1, 0, and 1, 1. Now just remember your DLD knowledge. Your DLD knowledge says that, if you want to address 4 slots or 4 positions or 4 addresses, then you need to have something like this. These are the 4 slots you want to address. So how many bits you should have? The idea will be, it will be clearly 2 raised to 2, right? So you require 2 bits. Similarly, if I want to find an address, or I want to give 16 locations, and I want to give each one of them independent identity. So again, I would put this equation. So that means n is equal to 4. So that means I need 4 bits to independently address 16 locations. So similarly, you can say if you have got 64, how many bits you would require? If you have 64 locations you want to individually address, then what is the minimum number of bits that you need? And minimum number, again, you can say that 2 raised to n is equal to 64. So their n would be equal to 6, correct? Okay, so now I have got this address of a particular location 0000, then 0001, 0010, 0011, so on and so forth. Now I want to map this address over here, right? Because you have to bring some data from main memory to cache, and take something back from cache to main memory. That is how the memory transfer works. But then, would say, okay, where would 0001 go? There is no 0001. I mean, there are only 2 bits. So how do you map an address which is given in the main memory onto cache memory? Well, so people figured this out. They say that, cache requires 2 address bits. So I will take the 2 LSBs and I will call this as index. And whatever remains, I mean, here, conveniently for us, there are also 2 bits which are left over. I would call it as tag. Right? So now this makes things simple for us. If I have 16, it is 0010. Again, it would start from 1000, then, 0101, and then, so on and so forth. So this pattern will keep on repeating, whether it's a 16 site address or it's a 64 or something. But if you just consider last 2 bits, it would keep on cycling from 00 to 11. And again, then, it would start from 00 to 11 and so on and so forth. So now the idea is very simple. If an address of memory location, the tag bit, the index bit is 01, then it will go and sit over here. Right? If it is 00, then it will sit over here. If it is 10, then it will sit over here. Or if it is 11, then it will sit over here. Now that's very convenient and very easy, but not so fast. Then someone would ask that, I mean, if I have 16 addresses, I would have several such things, which would have last 2 bits as 00. So it is given over here. So this one has 00, then this address has 00, this address has 00, this address has 00. And all 4 of them would say, this is my location, so I will put my data over here. So what it means is that somehow you have put data or instruction in 0000. And next one, if there is a jump statement or go to statement or whatever, you want 0100 address. You want to bring it from main memory and put it into cache. But the problem is there is someone already sitting there. That is 0000 address is sitting there. And now there is no other choice, because this particular address, because the last 2 bits are 00, it would insist that, this is my index, so I will sit only here. So if I want to give you a very simple example, now you guys are like 320 or 330 students in your class. Okay, so let us assume, let's make the problem simple. Let's say you have got 300 students in your class. Now, I've got only 10 chairs, right? And you have 300 of you. I'm assuming that, at any time, at most, 1 student will come, or 10 students, or not more than that, should come in here. It is for like, fee payment, and, you are called batch-wise or whatever. Now, there are 10 chairs, and then, there are 300 of you. So one thing is like very simple, that anyone who comes first can sit in any one of the chairs, and that is how we normally perceive. But, as we will see, that is also a possibility, but, it takes some time, because, a person would come and, has to look around from 10 chairs that, okay, which chair is empty? Let us go methodically. That, it says, okay, can I sit in chair number 0? No, can't, because someone is sitting there. Okay, can I sit in chair number 1? No, I can't. How about chair number 2? No, I can't. Someone is sitting there. He has to go on, or she has to go on making such comparisons. Now, but, we make things very methodically. We say that, you may have, and I give you a number starting from 0 to 300 or 299. I mean, let us make a computer science type of numbers rather than real life numbers. So your number starts from 000 to 299. And then, to make things simple, I say, just look at the last digit of your roll number. If your last digit of your roll number is 0, so that means 000 student has got last digit as 0. Then 010 has got last digit as 0, 020, so on and so forth. All of them have got last number as 0 or last digit as 0. And there would be 10 of them. So I would tell those 10 students that you can sit only in chair number 0. If chair number 0 is occupied, then you have to ask that guy to get up and you sit in there. Or you wait till that guy gets up and then you can sit in there. Even though the chair number 1 right next to it is empty, you can't sit there. Why? Because I want to make things very simple and very quick. So roll number with last digit as 0 will sit or will be able to sit in a chair only as 0 and nowhere else. Then last digit as 1 will be able to sit in chair number 1 and only 1. Even if the other chairs are completely empty, he or she cannot go and sit into chair number 0 or 2 or 3 or 4 or 9. Similarly, for all last digits starting from 0 to 9. Same way, here we are looking at last 2 digits. And why we are looking at last 2 digits? Because it is determined by the size of the cache memory. If the size of the cache memory was 8, then we would have looked at last 3 digits, right? And then only 1 digit would have been tagged. Now you may say, okay, my cache has asked for a memory address, says 0100. Probably there is some instruction or data in 0100. So my processor knows only cache. It does not know main memory. So it will come to location 00. And it says, oh, there is something in there. So I think, can it be 0100? The chances are 25%. Why 25%? Because there are 3 other candidates, like 0000 could be there, or 0100 could be there, or 100 could be there, or 1100 could be there. So how can my processor be sure that it has got 1000 memory address or 0100 memory address? After checking the index, it will have to check the tag. Only then my processor will be completely sure that it has got the right data or right instruction. Are you getting this? I hope you are understanding this, because this is very fundamental to understanding. Why are we doing this? Because we want to make things simple. Why this is simple? Look back at what I told you earlier, that my processor is working very fast. And I want my memory to be such that, just one glance at the memory would be able to tell you whether a particular address is there or not. So for example, if my processor asks a question that, I want something from the memory address, which is I want something from here, this particular address. It could be data or instruction. So as I told you earlier, since the size of the cache is 4, that is 1, 2, 3, 4, 4 slots, that means the last 2 bits will be called as index, and whatever others remaining will be called as tag. So here conveniently 2 bits are index and 2 bits are tag. So suppose if something is sitting here, right? And I'm not saying what, but there is something over here. So it just can't be happy that, okay, I found something, index 00 matches, there is something in 00. But, just hold on, just match the tag first. If the tag also matches, that means you have got the right instruction or right data. Otherwise, even though there is this index is same, but your tag is different, so that means it is some other location. It could be 0000 or 1000 or 1100. So that means you have not got a hit, right? Basically, it's a miss. Hit means you got your data or instruction, what you are looking for. If you don't find it, then it's a miss. So right now, don't worry about what valid is. We'll come to it later. Right now, only concentrate on two parts, tag and index. Okay. Now, you will start asking me question that what do I see as last two bits as XX? That is something, it requires some explanation. So let me. Okay. Now you have got, that memory is byte addressable, right? So that means you should be able to address each individual byte. That means 8 bits. Normally, when we talk about, say, normal ARM program and normal ARM data, it is of 32 bits. So if you remember, I showed you a figure that instruction number 0 would have 4 bytes, 1, 2, 3, and 4, right? So 4 bytes makes 32 bits, right? So then instruction 0, instruction 1, instruction 2, each one of them will have 4 bytes. So what we are talking about is, this is byte number. I'm just giving the last 4 digits of this byte. This is, okay, let me write it in decimal. This is byte number 0, byte number 1, byte number 2, byte number 3. This is byte number 4, 5, 6, 7. This is byte number 8, 9, 10, and 11. And then following would be 12 and 16 and so forth. Now, what happens here is that, instruction number 0 as it would start with address 0000. So you would only refer to address 0. Get me a word or get me an instruction from 0000, right? So that means it knows that it does not only has to bring this, but bring others also. So it has to bring not just 1 byte, it has to bring 4 bytes. Similarly, when I say bring me instruction number 1, it will bring not only 4, but 4, 5, 6, and 7. When I said bring me instruction number 3, it will not just bring byte number 8, but it will bring byte number 8, 9, 10, and 11. Now look at these figures. What is 0? If you want to write in hex, it is 0, 0, 0, 0. What is 4? 0, 1, 0, 0. What is 8? It is 1, 0, 0, 0. Next one would be C. What is C? 1, 1, 0, 0. I hope you still remember your hex code. So it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F, right? So that is like 16. So this is 1, 0, 0, 0. And then after that, when you come to say 16, it will be. So right, so this last 4 bits, if you look at this, it will cycle between 0, 0, 0, 0 to 1, 1, 0, 0. Now, if you look at it, last 2 address bits will always be 0. Correct? So that's why you also must have seen this trick in ARM instruction book. That's why we disregard for a given word address, we disregard last 2 bits. Right? Because they're always going to be 0, 0. It does not give you any extra meaning. So we don't consider last 2 bits. And then we say LSBs are actually bit number 2 and 3, right? Because 0 and 1, these 2 bits, we are ignoring because they're always going to be 0, 0. So they don't provide us any additional information. So that's why I have put XX over here. I'm assuming that this is a word addressable main memory, and this is word addressable cache memory. So last 2 bits I have ignored because they're always 0, 0. So it is better for me to take index bits from here. Now, this is assuming that it is a byte addressable memory. If I give you a word addressable memory, then you just assume that these are the 2 LSBs, and then you don't have to remove the last 2 bits. You have to remove the last 2 bits only if it's a byte addressable memory. So that would be made clear to you when an example is asked in exam. If I say that memory is byte addressable, then you have to consider that last 2 bits would be 0, 0. So you ignore them, and then these 2 things are given. But if I say the memory is word addressable, that means this is already ignored, and this is what you have. So forget about these 2. Is this clear?
Yes, sir.
Okay. Okay. So now we have discussed this. Now, someone may ask this question that why are you doing this? Isn't this waste of space? Just like, I gave you a very simplistic thing that, a student with last roll number digit as 0 can sit only in chair number 0. Even if chair number 1 is empty, or 2 or 3 or 4, or all starting from 1 to 9, all of them are empty, that student will not be able to sit anywhere else. He will be able to sit only in chair number 0. Why? Because his last digit is 0. The whole reason for this is simplicity, and you don't lose any time. Suppose I say, has student number 100 come? Then the person has to look only at chair number 0. If someone is sitting there, then match other 2 bits. So 0 is already there, so that means that shows his last bit. If his MSBs are 1 and 0, then say yes, 100 is there. He doesn't have to look at chair number 1, chair number 2, 3, 4, 5, 6, 7, 8, 9 and start matching tags and everything. So the time is less, and that is what we want. The first level cache should take minimum time to give you the answer that yes, I have it, or no, I don't have it. Right? So that is what is the main concern, and this is known as direct mapped cache. So the idea is very simple. Like, for example, if you want to say put these 4 addresses 0010 or 0110 or 1000, 1100, they all would gravitate over here. They would say, I want to sit here. Why? Because this is my tag 10, and this one, this one, this one, and this one, they are all tags. So then you will have your tag number over here, and sorry, 0110. So this, I think this is where it should go. So if you have this address, so that index is 10, then it can sit here, right? This one index is 10, that means this can also sit here, this can also sit here, and this can also sit here. The only thing different would be the tag. So then if there is some data in 10, you can't say for sure that it is 0010. It could be 0110, it could be 1110. So for that, you need to match the tag. So then, you will ask, what good have we done, right? Finally, if you want to find address which has got 4 digits in it, you need to find an address which has got all 4 digits which are correct. So if you want to find an address of instruction or address of data as 0001, then naturally it has to be all 0001. You can't just match 2 bits and say, hey, I found it. So in one way, we are not doing it, but this is more like divide and conquer. So if index is not present, then you don't have to search for tag, right? So you have saved half the labor. So if that particular index bit is empty, so if there is nothing in index number 10, and then I say, do you have 0010? The answer would be immediately no. Why? Because it knows that there is nothing in this index, so there's no point of matching tags because there is nothing there. So that means it is faster and speedier. Does anyone have any question or want to understand this in more detail? The concept of tag. So here we have understood 3 major principles. First one is, what is index? Number 2, what is tag? And number 3, what is direct map cache? Does anyone have any question?
Hello, sir.
Yes.
Sir, how processor will know that in this address only there is no data, because there can be more than one address where there is no data. So processor have to store the remember all the address where there is no data.
I'm sorry, I'm not able to understand your question. So let me put it this way. Suppose your instruction is, say, store type of instruction, right? So basically, you are supposed to store something in a particular memory location. And so now, suppose it asks you that, it want to store something in memory location number 0010. Okay. So now it would look here. That is 10 present, some data is there, then I can go and change it, or I can just write it over here, it is empty, and then it will go in over here. Let us assume there is something over here. If it finds over here, then it will try to match the tag. If tag also matches and index also matches, then it knows that particular data is here. So for loading, this is very much required that it got the, and where would it gets its location, that where it needs to get the data from, or where it needs to put the data. Well, that comes from your program and from your compiler, and then finally from your operating system. So processor does not have to remember anything. Processor gets, just like you are giving your instruction that store something, and you give some memory location, and then your compiler figures out, compiler knows where the data will be stored. So it starts giving number, because you as a writer of the program may not too much know the memory map. For you guys, you are lucky that the initialization of the memory and everything, that code is already done and already written. You are writing only the middle part. So initialization code, actually, if you go to your Kyle compiler and see, it's a long code. And there, it initializes, it defines where is the usable memory. So those things are given. And you are writing just a code which is the middle part. And that is good, that it saves you from writing lots and lots of lines of code for doing some simple task. So does that answer your question, or because I have not understood what exactly bothering you? If you can explain it to me again.
No, sir. Actually, what I am saying that in main memory there can be more than one address, like 0010 is empty, and 1010 can also be empty. Means both are empty at the same time. So means how processor will know that these both address are empty, which consists of no data.
Okay, actually, processor does not care what addresses are empty or filled in main memory. Processor only cares for cache, because processor doesn't know anything beyond cache. So what you are talking about is main memory, right?
Yes.
So main memory has got something beyond it, which is called virtual memory or your hard drive. So just like we see a dialogue taking place between main memory to cache, the same thing happens between virtual memory and main memory, right? Because virtual memory is much, much larger than your main memory. Your virtual memory is 1 terabyte, whereas your main memory is only 8 GB, right? So there very similar mapping has to take place. So that thing is taken care of by memory management unit. Processor only asks up to cache, instruction cache or data cache, that, I want this instruction or I want this data. And then, it's the job of memory management unit to manage it.
Okay, sir, I got. Thank you, sir.
Okay, so if someone is asked instruction 01 fetch 000 address and then instruction 2 fetch 0100 address, then how processor will handle that situation? So, okay, so I believe what you are asking is that, the index is same for both. I think that's what you are, Harsh, if that's what you are trying to ask, that, this is the index. And, at this index, 2 instructions are trying to sit. So first instruction, which is already sitting, is 00 and tag was also 00, right? So now this is fixed. Now processor is asking for 0100. So tag is 01, but index is still 00. So when it comes here, it sees that, oh, index is there. There is something in there, but it finds out that tag is not matching because here it is 00, but your tag has to be 01. So it is called a miss. So then a message will be sent to main memory. Then, okay, get me 0100. So it finds out 0100 and puts it over here, kicks out this 0000. And now next instant it will be 00 and tag will be 01. And then it will be given to the processor. It is not a nice thing not to have a hit because processor will have to wait twiddling its thumb till the shifting of stuff from main memory and you bring it to cache memory because whatever cache processor wanted was not there in the cache, right? Does it make sense? This is how actually that is the principle of how processor works, because you can be damn sure that since there are so many more locations in main memory as opposed to in cache, there is bound to be conflict in direct map cache, that at least 4, or this were like 64 and 4. So that means there will be total like 16 addresses which would be sitting on just one location. So tag would be different, index would be the same for 16 instructions or data. So if any one of those 16 are called, then it will have to kick out other and sit here. So they cannot sit together at the same time in one location. So only one of them can be present in main memory, in cache memory, and others will have to sit in main memory. Suppose by chance, if you have written a program which accesses first, say 0000, then it accesses 0100, then it accesses 1100, and then it accesses 1000. That is going to be a killer, right? Because they all want to sit in the same index. So initially it says, okay, get me 0000. So let's say initially everything is empty. So it first goes to main memory, brings this data and puts it over here, or instruction, whatever you want to call it. After that, it says, okay, now I want 00. I'm sorry, I want 0100. Well, it has to sit here. And this is, when you match the tag and index, it is 0000. So this is not what you want. You go to main memory, get 0100, and then put it over here. So till then, processor will have to wait till this instruction comes in and changes the tag to 01. Then the third instruction which you want is 1000. Again, processor comes here, says, okay, get me 10. And then, say, no, sorry, tag is not matching. Tag is 0, 1. You want 1, 0. So again, this will have to be thrown out and, this new thing would be brought in, so on and so forth. So it is going to waste a lot of time. So that is the unfortunate feature of this direct map caching. Okay, but the advantage still is that it is very fast and that's why it is kept. So first level cache in your laptop or in your mobile is always direct map cache because it is very fast. It is very inefficient. That I agree. That, I mean, you're asking 4 instructions. Your program is jumping from 0000 to 0100 to 1000 to 1100. Right? So all 4 of them could have sit here if there was free sitting. Right? There are 4 locations over here. So it can sit here, 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 and here. But no, that's not allowed. They can sit only in one location. Why? Because they have share the same index. So that's the unfortunate part. Any other questions?
Hello, sir. I'm having a question.
Yes, Taran.
Sir, my question is, sir, when a memory block, when data from a memory block is fetched to the cache, then the tag is also brought from that memory.
I'm sorry. Say that again, please.
Sir, when the data is brought from a particular location in main memory to the cache, there the tag is also brought at that time.
I don't understand. Because see, if 0, 1, 1, 0, this particular thing, if it has to sit here, then first you look at the index 1, 0. So this is 1, 0. Then it can sit here. Whoever is sitting here has to be kicked out, and this new data will sit here, and 0, 1 tag would be written over here. So whatever was here previously would be thrown out.
Sir, my question is, how will it know that the tag of that location was 0, 1?
Well, for that, you have electronic circuit to read, right? So for that, you have to write an RTL code and specify this. Thankfully for you, you don't have to do the connection like you do in breadboard. I mean, thankfully your behavioral description of a processor or a finite state machine would be directly converted into electronics for you. So for those things, you don't have to worry. Yes, but if you want to go down to the level of transistor, something is happening in the background in your tool, which will have to make sure that these things are read and removed. Right. So it's basically cleaning the data from a gate. How do you change a gate value from 0 to 1? It has to be wiped clean. So that means the proper value is to be NMOS and PMOS transistors. So if you know what that means. So
yes, sir. And sir, I'm having another question, sir. The tag value is stored at the word, right? So then the data will have only 30 bits to store, right, sir?
No, the table does not have to be total 30 bits. The table size would be say data of 32 bits plus whatever the number of tag bits and plus valid bits. So it could be 37, 38, 40, whatever. Because all these things don't have to be transported. Once you match the index and tag, and if they are matching, then you only have to transport data. You don't have to transport tag and other things.
Sir, my question is, sir, that here the cache is word address, right, sir?
Yes.
That means at location 00, we are having just 32 bits to store our data, right, sir?
Right.
And if the tag is occupying 2 bits over here.
That's what I'm saying. This is 32 bits. Okay. This is, in our case, is 2 bits. And valid bit is 1 bit. So your table size is 32 plus 2 plus 1, 35. You don't worry that this is 35 because you don't require 35 data lines. Because once the tag is matched and index is matched, then all you need to do is bring this 32-bit data. Then you don't need tag or anything. Are you getting my point?
Yes, sir. Yes,
Table
sir.
size, in fact, I will show you that, in uh, SAT associative cache, you can have 2 tags per index. Then, the table size would be 68 bits, or it could be 128 bits. So the table size does not matter, because at a time you'll have to transport only 32 bit of data.
Yes, sir. I got your point. Yes.
Yeah.
Thank you, sir.
Okay, so things would become clear as we go further. So let us complete this topic of figuring out what is the size of tag and what is the size of index. So now the question to us is, find out tag bits and index bits. So that means how many tags bits should be there and how many index bits should be there. So the first rule is number of bits required to address all locations of the cache is equal to index bits. 2, number of bits required to address all locations of main memory is equal to total number of bits. And tag bits is equal to total number of bits minus index bits. Okay, so let us take a practical problem. Okay. So now someone tells me that, I have a cache size of 8K. Main memory size of 1 MB. Okay. So now, what is the overall tag bits? What is the overall bits, tag bits, and index bits? So index bits by definition is what? Number of bits required to address each and every location in cache. So in cache, there are 8K locations. So 8K is what? I always tell you that you must remember this. 2 raised to 10 is 1K. 2 raised to 20 is 1M. And 2 raised to 30 is 1G. So this you can do things very clearly. 8 is 2 raised to 3 times 2 raised to 10. So that is equal to 2 raised to 13. So that means 13 bits are required to address each and every address of cache. main memory size of 1 MB. So that is equal to 2 raised to 20. So I would require 20 bits. So now I got the answer of index bits, that my index bits is equal to 13, which I found from here. Overall bits, that means the total address size is 20 bits, and tag bits is equal to 20 minus 13, that is equal to 7. This is very important. Does anyone have any question? Okay, someone gave a correct answer. So this is how it is. Now, you can imagine that if I say that I'm keeping the size of my main memory as the same as 1 MB. What if I increase the cache size from 8K to 16K? What would be the change? Would there be any change in overall bits? The answer is no. Why? Because main memory size has not changed. Will my index bits change? Yes, of course it will change. Previously it was 8K, now it is 16K. So 16K is 2 raised to 4 into 2 raised to 10. That is equal to 2 raised to 14. So that means my index bits would be 14 and my tag bits would be 20 minus 14. That is equal to 6. So that is how you can play it like accordion. So overall bits is totally determined by the main memory size. Index bits are totally determined by your cache size, and tag bits is the difference between the two. So difference between the overall bits minus the index bits. Does anyone have any question? Okay. Now, let us see the problem of a direct map cache. So you are looking at address which is given in decimal as 0, 1, 2, 3, 4, 3, 4, 15. So in this order, you are requesting the references. It could be data reference or it could be instruction reference. And these things in binary would be 0, 0, 0, 0, 0, 0, 0, 1, and so on. Again, my cache size is the toy size. It is 0, 0, 0, 0. And first demand is coming from my processor says, I want address 0, 0, 0, 0. Is address 0, 0, 0, 0 present over here? No, the answer is no, right? Because why? Because there is nothing there. It is completely empty. So it will be taken as a miss, right? Processor asked for a particular address. It was not found in the cache, so it's called a miss. So what we'll have to do from some next lower level, which let us assume is main memory, it will have to go and get this address 0000 and put it over here. But put it over here means where will it put? As you know, the index bits are 0001, 1011. So look at this. The index bits are 00. So only place it can sit is here and nowhere else. So this is your miss. You got the data, and your tag is again 00. Tag is same as index because index is also 00. Tag is also 00. Now, second one is the processor asks for address 0001. Now, of course, 0001 is not here. So it will have to go to main memory and get this particular address. And if after getting is, where will it sit? It can sit only here, right? Why? Because index wise, if you want to write index, I'm not writing index, it is just assume that it is there. But for your own understanding, you can write 0001, 1011. And of course, as we know, the index bits are last 2 bits. So 2 bits, so here are the last 2 bits. So this is all index. Okay. So now the next one is 0001. Your processor will immediately look at this particular index 01. Well, there is nothing. So what we will have to do? Go to main memory and get that data. And then of course, that is also counted as a miss because you wanted it, it was not there. And then finally you got it. So you placed it in 01 index. Tag is same as 00, just like here. For 1 also there is a 00 tag, so we have put it over here. Similarly, now we want 2. Just 1 second. Someone, sir, what if the cache memory is not a power of 2, like 10K? Normally, it is better to have. It is like, for calculation purpose, it is better to have something of the order of 2. So 2 raised to something. So it is, you will rarely see an odd number that, I have got 19 gigabytes of memory because it is like, it's difficult to address. So then, you have to have more address line to show these smaller address lines. So someone says, I have got only 10 addresses, but to refer to those 10 addresses, you require 4 bits, right? So there are total 16 possible addresses, but out of which you are using only 10. So normally it is not done. Okay, coming back to this. After 2, I wanted 3, which is 0010. So again, there is nothing in 10 location. So it is again called a miss. And the tag once again is 00. As you can see, the first 2 bits are 00. That's put over here and it is brought in here. Then I want 4. Tag number 11. Is there anything there? Nothing. So in tag number 11, I will go and put this location number 4 or memory address number 4. And it will go and sit here. But the tag bits are still the same, all 00. So it is here. Now I want 3. So thankfully, thank God. What happened? I got 3 and it is so after 4, okay. So after 3, it is sitting here. I'm sorry. I just went ahead. I wanted 3 and 3 is 0011. This is 3. Let us just, to avoid confusing ourselves, if not all of you, then at least me. And this is this, 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 and so on. So 3 sat here with index as 11 and tag as 00. This memory 3 is here. 4. Now you have to see what is 4. 4 is 0100. So let us go to index number 00. Is there something there? Yes, there is something. But then look at the tag. I want tag 01, but here the tag is 00. So again, it is called a miss, and I will have to throw this data away, and I will have to bring in the new data or new instruction and put it over here. Right. So now this tag number has changed. Of course, index will always remain the same as 00, but the tag number 01 has come. Now you want 3 again. Thankfully, it's a hit because 3 is already there. It is sitting here. So, your program is very happy. It does not, your processor does not have to wait. Then you want 4. Again, it's a hit. So it is 01 and then, it is 11. But then, suddenly you had a go to statement which says go to 15. So it is 1111. So that particular thing in location number 11, your tag, there is something there, but tag is different, right? Tag is 00. So that is not what you want. So you throw that away, bring it something from memory location 1111. So you put it over here and change this tag from 00 to 11. So that is again a miss. So you saw that in this program, you made 8 requests and you had just 6, you have 6 misses and just 2 hits. Not a very good thing. So let us come here. And now I'm doing something clever. I'm doing something clever means when my processor makes a request for a memory location 0, I not only get something from memory location 0, but I also get something from memory location 1. Right? So 2 together. So the first same thing over here. Now look at the, I wanted to keep my size of the memory same. That means 4 boxes. But now I'm doing something which is slightly different. So 4 boxes are sitting like this. And so my index has shrunk. So now my index will have only 2 bits. And those 2 bits would be 0 and 1. Right? Rest would be your index. So in the first thing, I want 0, 0, 0, 0. I not only got 0, 0, 0, 0. Of course, it was a miss, but I got this and this. Right? Why? Because I made a choice that I will not only bring 0, but I will also bring its neighboring. So that means I got this. Then, second one is a hit because there is a memory reference to 1. So it is a hit. Then I wanted 2. So then, in 2, this was a miss. So I got the new one. Then, it was the 3 was called. So it's a hit. And then, you can go and traverse this. So what have we learned? We have learned that instead of getting just one at a time is not good. You should get 2 or more addresses together. And what are we taking advantage of? It is clearly given here that we are taking advantage of something which is known as spatial locality. That means after 1, 2 will be used. And you know from experience, the way you write a program, that after 1, most of the time, instruction number 2 will be done. Then after 3 will be done. Then 4 will be done. And then 5th will be needed, unless you have a loop statement or a branch statement. So that's why instead of bringing just one word, you bring a block of words, right? And why you want to do that? Because you believe in this spatial locality. That instead of 1, you say, oh, I want 2 together, or I want 4 words in a bunch, and I want to bring it. I want 8 words in a bunch, and I want to bring it, or 16, or whatever size you want to keep. So if you want to have an equivalence with, say, your breakfast, say you are doing breakfast and you don't know how hungry you are. So you go out to the baker's store and get one slice of bread. You put it in the toaster, make a toast, butter it, and then eat it. Then you feel, oh, I'm hungry again. I'm not full yet. So you go back to baker's store, get another slice of bread, put it in the toaster, and then toast it and butter it and eat it, and then again go out till you are filled. What is the disadvantage? Well, you will say, of course, you have to go to 6 times to the baker's place to get one slice of bread. Yeah, that is the disadvantage. What is the advantage? Well, advantage, if you want to call it that I got just that much amount of bread which I needed and not any more. Fine, not a very big advantage. Then you said that, well, what if you had brought 2 breads together instead of just 1 slice? If you had brought 2 slices together, then you would have to make only 3 trips to the baker. Then you say, how about if you're making 4 slices together? Then you will have to make 2 trips. In first trip 4 slices, then second trip 4 slices, out of which in the second trip you got 4 slices, but you ate only 2 and 2 were remaining. So then someone may say, okay, how about 8 slices together? Fine, then you just have to make 1 trip. What about 16 slices together? Well, you will have to make only 1 trip, but you will eat only 8 slices, and 8 slices would be remaining, or you will have to throw away depending on whether you are going to use it again or not. So this brings us to a very important concept, which is known as bringing a block of memory. So that means you're not just bringing one word, you are bringing several words together. And why you are doing that? because there is something which is known as principle of spatial locality, and which you yourself have tried in your own programs, that after an first instruction you execute second instruction, third, fourth, fifth, unless there is a loop. So that is called the principle of spatial locality. And more importantly, we have understood the concept of block. This block is also called as cache line. I mean, the different words in different literature. So people call it block and some call it cache line. So how many words per block? Right, this is also a question. So it is like a question which is asking to a person who is doing breakfast that, how big a bread you want to have. Because, when we go to a baker's place, now, we've got a choices of like 3 sizes. One is like a small size, then medium size and a large size of loaf. So if you are alone, then, you just get a small size loaf. So you don't have to throw away or waste bread. If you are a medium-sized family, then, you get medium-sized loaf. If you're a very large family, then you get a large size loaf. So similarly, this is a question which we will be discussing in the next class. That, should I have 4 words per block or 16 words per block or 64 words per block, and how do we decide? One thing would be very clear that, someone has to do statistical analysis, because I'm designing a general purpose processor for you, and I'm not sure what kind of programs you would be writing. You would be writing a program for, say, graphics. You could be writing a program for word processing. You can be writing a code in Python. And, everything, in its assembly language would be coming out in different number of instructions. So in short, if you have a code which is going for a long time, large number of instruction, and then only a loop, then it makes sense to have a larger block size. So more instructions per block or more data per block. If your program has too many loops, then you say it is better to have small block size. So you guys have 4 words, 8 words. But how exactly to determine? Because, different people are going to use different things. You are not making your processor only for graphics or only for gaming or only for word processing, right? Your processor should be able to do everything. So we'll see how do we statistically decide how many words should be there per block. Okay, so, and then, we will also see that, my overall address will now have 3 parts. This is my overall address. This would be my tag. I mean, the sections are random. This is tag. This is index. And this is known as block offset. So that means if I have 8-word block, then my block offset will be 3 bits, right? Which word within a block do you want? So I mean, at least I need 3 bits to determine which word from this block of 8 words I want. So this is your overall address would still be determined by your main memory size. But, cutting off, calling something as tag or some bits as index and some bits as block offset will be dependent on what is your block size. If your block size keeps on increasing, then your index size keeps on decreasing. So if you have a large number of words, then, your block size, the block offset would be large, and then index would start shrinking. There will be less indexes. Those things we'll see in the next class. Now, one more thing, I want you to start preparing, because you may have a pop quiz on Thursday, a small 10-mark pop quiz. So I want you to start reading whatever I have told you. Go through my lectures, the pages are given, and you can clarify your doubts in Wednesday's lecture, because I feel that some of you are not regular. So having a 10 marks quiz would do you good. I mean, don't start asking that, how many percentage you will do. I mean, I may have several quiz and then, probably it would have 10% of the weightage, but 10% is a lot. So I will tell you the exact percentage, but in your mind, be prepared for a 10-minute quiz on Thursday. Most probably it will be there. If I feel that by Wednesday I've not been able to cover enough things, then there won't be a pop quiz on Thursday. But you will have to be prepared, because I won't tell you, right, whether there is a quiz or not, because I want you to continuously read and prepare. Because if you continuously read and prepare, it would take you only 1 hour after the lecture or end of the day to just refresh your memory and make your notes. And then, you won't have tension at the last moment that, I have to read so many pages and so many concepts. Okay, any questions from your side?
Hello, sir.
Yes.
Sir, here in example, sir, can you please go to previous slide?
This one?
Yes, sir.
Okay.
Sir, here if we encounter 0, 4, 8 like that types of instructions, then we will always means we will always miss that instruction. We cannot find it in.
Right. So the whole idea is that, if two instructions or two data has the same index, it will be kicking each other out. Right? For direct map cache, indirect map cache, that is important. That if two instructions or two data has the same index, then they would be kicking each other out. They cannot coexist in cache. Okay.
Yes, sir. Okay.
Okay. I mean, we'll discuss it further in the next class.